Okay, thanks. So yeah, so this is restricted invertibility. And this is joint work with Dan Spielman. So basically, so let's start off by asking a very basic question about matrices. So suppose I have an n by n real matrix L. So this defines a linear map. X goes to Lx. And one basic question about this matrix is this function, is this map injective? So is this thing invertible? So we say L is invertible if x not equal to 0 implies Lx not equal to 0. Okay, and this is seen as some kind of non-degeneracy property of this matrix, and it's one of the first things you want to find out about a matrix if you have one, maybe. So not every matrix is invertible, but one of the first things you learn in linear algebra is that every matrix has a submatrix of its columns, which is invertible. So in particular, if if S is some subset of the columns that is linearly independent, then LS is invertible. Okay, so this if you restrict all the coordinates to just the things in S, then this thing is injective. Okay, and the one-line statement of this is that the one of the first things you learn is that the size of this subset S, the maximal size of the subset S is equal to the rank of the matrix. So every matrix contains a submatrix of its columns of size equal to the rank, which is invertible. Okay.
LS is not square.
Well, I just mean that this function is I just mean this thing. So it's just a restatement of the thing that it's linearly independent, basically. Yeah.
Except when the matrix is all zeros.
Okay, yeah. If the matrix is all zeros, fine.
Yeah.
Okay. Okay. Yeah. That's true. So okay. So basically, the rank captures this question about, given a matrix, what's the largest submatrix that's invertible. So one of the there is one problem with this sort of notion of degeneracy, and this nice statement which I just gave you, which is that invertibility and rank are both very fragile notions. So example, if I take this matrix, L to be just a bunch of 1s, then this thing has rank 1, and you can't even pick two things that are linearly independent. But then if I add like some tiny amount of noise, I suddenly get rank equal to n, and I get that this thing, the whole matrix is invertible, right? And fundamentally, the behavior of this thing as an operator is not really very different from without the noise, and so this thing is still really degenerate, yet it has full rank. So this is somehow not a quantitative enough notion of degeneracy. So to remedy this situation, we can define the least singular value of a matrix to be the minimum of the length of Lx divided by the length of x for non-zero vectors. So this is a measure of how much L can shrink a vector. Okay, and we say that L is well invertible if its least singular value is bounded away from 0. So it's bigger than some constant, which some absolute constant, let's say. So this thing is far from being singular. Okay, and so it's not true that every matrix has a submatrix of size equal to its rank, which is well invertible. Just consider this example. the largest well-invertible subset has only one column. But there is another notion called the stable rank, for which we might hope such a statement, could hold. So define the stable rank of a matrix L to be the Frobenius norm squared divided by the 2 norms squared. Okay. So this is the sum of squares of all the entries. This is the square of the largest eigenvalue. Okay.
Why would this have something to do with rank?
Well, so this is a relaxation of rank, right? So this is something like the sum of the singular values squared divided by the max singular value, and you can see that this is at most. This is always at most the rank of L. I mean, part of the content of the theorem that I'm about to show you is that this is a suitable. This does have something to do with the rank because it measures the size of the largest well-invertible subset of a matrix.
What's a singular value?
Sigma squared in the denominator?
Yeah.
You just don't have it on board.
Oh, okay, yeah. Huh? Okay, I didn't define that. Fine. So it's a sum of.
No. Just add a square on the denominator.
Oh yes. Here. Yes. Sure. Well, I mean, in any case, there's some relaxation of the rank. Can you see why this is at most the rank? I mean, yeah. So the. Okay. So the thing we might hope is true if we actually want this to be a reasonable notion of rank, is that every matrix is well invertible on a subset of its columns of size equal to the stable rank. Okay. And this is exactly the theorem that Bourgain and Tzafriri proved in 1987. They proved that given some matrix, some n by n matrix with unit length columns, there exists some subset of the columns of size at least equal to some constant times n divided by divided by the 2 norm of L squared, such that the least singular value of this thing is at most some other constant. So C and D are universal constants. Okay. So this is not exactly what we wanted. It says that you can get a set of size proportional to the stable rank, which is well invertible. Okay.
Can you define again? What's a singular value? What are the
Singular value is this thing. It's a minimum of normal. It's how much L shrinks a vector.
It's a minimum singular
It's a minimum singular value.
all the singular values, so just say.
These?
Yeah, all the sigma i's. So we just say.
You don't need sigma I for this actually, but
For the definition.
for this?
For this.
Okay, fine. So
The eigenvalue.
sigma I squared is ith eigenvalue of LL transpose. Okay. So
What are the dependencies in this theorem? So you have a G and a CD.
C and D are some universal constants.
Oh, that's not one but two different points.
That's a comma between
That's
the
a
C.
comma between
Yeah.
C and D. Okay.
Yes.
It's useful.
So if you give me a matrix with unit vectors, then if the operator norm is bounded, there's a large set that has large least singular value. Okay. Now I can show you a bunch of extreme examples to sort of extreme examples to show you what this theorem says, and that it's sort of tight. So if I take an orthonormal basis, then so if I just take the identity, then I have n over the operator norm is equal to n. So I get a set of size some constant times n. So this is tied up to some constant. If I take a bunch of copies of, if I take a bunch of orthonormal bases, and I mean I can make this square by whatever, putting in some larger dimension. The squareness doesn't really matter. Then I get that the stable rank is n over k if I have k different k orthonormal bases, k copies of the identity. And so, the best I can do is pick one of these. And again, the theorem tells me I can get that. And for this degenerate case here, it tells me that I can extract, something of dimension c. So c is some constant less than 1. So I can extract one vector, which is, well invertible, which you can always do. Okay. Another way of looking at this theorem is that it's sort of a coordinate version of the following fact. So if I take a matrix L and then I look at the matrix LL transpose, then this is some positive semi-definite matrix that maps the sphere into some ellipsoid. Okay. Now, what this theorem is saying is that if none of these, so if I know that, so the largest axis here is the largest singular value, also equal to the 2 norm. So, the largest axis here is the 2 norm squared of the matrix, and the least is equal to the least singular value. Okay.
Just the 2 norm, not square.
Of this is LL transpose. But so by the fact that these things are eigenvalues, I can just use if I know that this thing is bounded by some constant, just by Markov's inequality, I can conclude that there are a bunch of eigenvalues that are bigger than So just by Markov's inequality, I can conclude that there are k singular values, sigma I squared, that are bigger than 1 minus epsilon times. I'm sorry, that are bigger than epsilon for k bigger than something like 1 minus epsilon times the stable rank. This is just Markov's inequality. It's saying that if the max is not too big, then and the average is kind of big, which is this quantity, then there must be a bunch of things. There must be a large number of directions which are big enough. And then if you restrict this matrix to these dimensions, then just to the span of these eigenvectors, then all the singular values are bigger than epsilon. Okay. So what Bourgain-Tzafriri theorem is saying is that so restricting to k singular values corresponds to restricting to top k eigenvectors. So the point is that the eigenvectors in general are not they're not coordinates of the matrix. The eigenvectors are some other vectors. So what Bourgain-Tzafriri is saying is that I can actually pick a section along these coordinate axes, which is big in every direction. Okay.
You would say at least epsilon times sigma max squared?
Yeah.
Because the second condition is scale independent, but the first one is not.
Oh, okay, fine. So this would be well, really, you can get the average here. You can't get the max. You can get the average here. So you'll get something like this. That's true. Okay. So you can see this as a coordinate version of this, simple calculation, basically of Markov's inequality applied to, eigenspaces, eigenvectors. Okay. Okay. So this was proven in 1987, and there were a series of works by various people, including Verschijnen in 01. I guess I should say Bourgain and Tzafriri in 91, and then Kasatza and Sarek and a bunch of people who improved the constants C and D in that theorem. So originally the constants in that theorem were something really tiny, like 10 to the minus 72 or something like that. And ultimately, if you add all this stuff up, you get something. You get the following slightly more general theorem. So if you have any rectangular matrix n by m, where m is bigger than or equal to n, and any epsilon bigger than 0, then there exists some subset of size at least some constant depending on epsilon times the stable rank, so that the least singular value squared on the subset at least some other constant depending on epsilon times the average length of the columns. Okay, so now, so this does a couple of things. It removes the assumption that the columns have unit length, and it gives you this parameter epsilon, so you can adjust these constants depending on whether you want a big subset or a small subset. So for example, it's known that you can get d epsilon equal to 1 minus epsilon, so you can get arbitrarily close to the stable rank. But then you need to take c epsilon to be something like some constant times epsilon squared, but this is again some really tiny number. It's known that you can do this in, so if you want c epsilon to be equal to, so if you want to get arbitrarily close to the average length, if you want this thing to be 1 minus epsilon, then you need the singular value to vary as something like epsilon to the log epsilon, something like that.
Assume that every column is a unit vector?
No, so this doesn't assume anything about the columns anymore.
Divided by m, what was the
m is the number of columns, so it's n by m.
Okay.
If one of the vectors is extremely short, then the minimum singular value will be 0, right?
Oh no, this is of the restriction. This is of this restriction. So this kind of captures this. So if all the vectors are short, then you definitely can't do anything better than whatever the length is. But some of them can be short. As long as on average they're long, you can get this matrix. Okay. And so then there is some other version of this which I believe gets us with 1 over 128 and 1 over 8 root pi something or other. This is due to Trop. But basically, in different regimes, there were sort of quite different proof methods used to get these different constants. I mean, they're all based on Bourgain-Tzafriri's original thing, but they involved different. You had to do additional things to get these numbers. Okay.
Just slide that up.
Huh?
We'll just pull the board up.
Oh, that's a good idea. Yeah, I've never used one of these before. So, okay. So what we showed in this work is you can take c epsilon to be epsilon squared and d epsilon to be 1 minus epsilon squared for all epsilon. And we have like a simple proof, simple constructive proof that doesn't use any facts about anything. I mean, just uses linear algebra. So these original proofs use some functional analysis and probability kind of stuff, and it was pretty hard. And it's deterministic, and it takes O of n to the 4 time if you care to, compute this. And actually, people do care to compute these things in numerical linear algebra. I mean, given a matrix, it's sometimes desirable to extract some well-conditioned submatrix that sort of represents a matrix. Okay? There are no constants.
But if you want c close to 1, you could just take epsilon plus 1.
Yeah. So there are no hidden constants, and it's known that this epsilon square dependence is necessary. So there's some example involving some Hadamard matrices that says that you need, if you want to get this thing arbitrarily close to 1, you need this thing to go as epsilon squared. So essentially, these are the best possible bounds. Okay, so I guess I'll show you the proof of this theorem.
There is a conjecture about partitioning.
Yes, yeah. So I should mention that the original motivation for Bourgain and Tzafriri was, so once you have this thing, given any matrix, you can iterate this log n times to partition the columns into well-conditioned subsets. Okay, and this is related to something called the Paving Conjecture, which is a sort of very old conjecture in functional analysis, which asks if given any such matrix, you can partition into a constant number of submatrices that are well conditioned. So this has a lot of implications, and this is seen as a step towards doing this. So if you iterate this, just recursively, you can because the set is a constant size of the stable rank, you can prove that in log n iterations you get a partition into well conditioned subsets. Okay.
Is the non-coordinate version of that easy to see?
The non-coordinate version of that. So by the non-coordinate version, you just mean if you have a diagonal matrix, essentially.
Oh no, you get to choose non-coordinate subspaces.
Yeah. So I guess.
One way of bucketing the eigenvalues.
But then the last.
Well, if you choose non-coordinate.
You want to take.
You only wanted the sigma mean.
But then one of the buckets will contain the sigma min. You probably want to uncorrelate with all the sigma min.
If you choose, no, I think the right thing to do is to choose a subspace that is not an eigenspace, actually. So a random subspace, for example, I think that would cut all of the eigenvectors, basically. You wouldn't have any. I think that would be the right thing to do. Okay. Okay, so I'll show you proof of this theorem. So here's a sketch, not a sketch, just sort of an outline of how this proof is going to go. So let me set up some notation. So suppose the input matrix n by m matrix has columns that I'm going to call W1 through Wm. Okay. Now it's sufficient to okay. So here's how we're going to select the columns. We're going to keep track of a couple of things. We're going to keep track of a matrix A, which is initially going to be 0, and we're going to keep track of some real number b, which is initially going to be at some value b naught. So the picture is going to look like, we're going to start off, this is the real line, you have some number b, and you have your matrix A, and these x's are eigenvalues, all the eigenvalues are 0. Okay? And what I'm going to do is I'm going to take some steps, and in each step I'm going to add one of these vectors, one of these columns. I'm going to add its outer product with itself to A. So after one step, A is going to be equal to Wi1 Wi1 transpose. Okay. So what's that going to do? Well, so initially A was a 0 matrix. If I add a rank 1 matrix, it's going to end up with one positive eigenvalue. I'm going to ensure that this eigenvalue lands ahead of B. Okay. Then I'm going to move this B back by a fixed constant to some value B minus delta. Okay. So after one step, I have A equal to this rank 1 matrix, and B is B minus delta, or I guess. Okay. And I'm going to iterate this k times. So in the second step, I'm going to have A is equal to Wi1 transpose Wi1 transpose plus Wi2 transpose. So now I'm going to have two non-zero eigenvalues. So in the second step, I'm going to ensure that this new eigenvalue, also falls to the right of my current B, which is going to be B minus delta. And then B is going to be, B minus 2 delta now. So I'm going to move this back again. Okay. And I'm going to do this for k steps. Okay. And at the end, I'm going to have A is going to be the sum of indices in some set, Wi transpose. B is going to be is going to have the value B naught minus k delta, right? And I'm going to maintain the invariant that every time I add one of these outer products, my new eigenvalue jumps across wherever the barrier is. Okay?
And the old one stays where it is, I guess.
No, the old ones are also going to move in some manner. But every time I add a vector that's not in the span of the previous vectors, I'm going to get one more non-zero eigenvalue. I'm just going to ensure that that jumps across the barrier. The old ones only move forward. The old ones will move, but because I added a positive semi-definite. So the eigenvalues, the old ones will never move back. There's this interlacing. I'll talk about it.
Because you're adding a positive semi-definite matrix.
I can explain. I'll explain that in more detail in a bit. Okay. So
you will always add a linearly independent column.
Yes, I'll always add a linearly independent column, and at the end, at the end, I mean, what is this thing? This is just going to be equal to LS transpose, right? And at the end, I'm going to have that all the eigenvalues that the kth eigenvalue of A is at least it's going to be my target, whatever, 1 minus epsilon squared times the Frobenius norm of L squared divided by m. So at the end, I'm going to ensure that all the eigenvalues of A are bigger than this, which means the singular values squared of this are bigger than that. So L is my original matrix. I'm choosing vectors that are columns of L. At the end, I have A, which is the sum of some outer product of these things. So it's going to be LS transpose. Okay. Okay, and the way roughly I'm going to get this number is that so what's going on, right? So initially, I'm going to have B naught is going to be roughly equal to the Frobenius norm of L squared divided by m. This is the average length. Okay. The step size, this thing, is going to be roughly equal to the 2 norm of L squared divided by the length. Okay. And so if I take a number of steps, if I take k that's something like the 2 norm of f squared divided by the Frobenius norm divided by the 2 norm, this is the stable rank, times epsilon squared, let's say, or times some small fraction of this, then by these scalings, the place I'm going to end up is going to be about that number. Okay? So the rate of moving back is controlled by the 2 norm. The place where I start is controlled by the Frobenius norm. And so the number of steps I can take, before while still staying away from 0 is something like the ratio of those two numbers, which is the stable rank. Okay? So what I'm going to prove is that this can be done. Like there's always a suitable vector. Given any matrix, you can always choose a vector in the next step that lets you do this. And then
So the n to the fourth comes from searching this word?
Okay, so they're going to be like n steps, and each step you're going to need to do matrix inversion. And matrix inversion is really the big and then okay, I mean naively it would be n to the fourth m or something, because then you would search m, but then maybe you can do some tricks with right. Actually there should be an m in here in any case. It's not, it should be n cubed m or n to the fourth m. I guess you can do some tricks with rank 1 updates to get rid of one of the n's, but anyway. So whatever, it's pretty slow, but it is deterministic polynomial time, which is okay, I guess. So okay, so that's a broad outline of the proof. Now let me write down. Okay, so given that this is how I'm going to do this, the basic thing, the first thing I need to identify is, suppose I have some matrix and some A and some barrier B, right? When is my, and suppose I want to add some vector W, when is the new eigenvalue going to jump across B? Okay. So I'll write some definitions. So I'll say that, okay, so let A have k non-zero eigenvalues all bigger than B. Okay. Then I'm going to say that some vector W is B good if A plus W transpose has k plus 1 non-zero eigenvalues all bigger than B. Okay, so this is just that the vector is good if it gives me a new eigenvalue that's bigger than B. Okay. Now there's a simple lemma which I'm going to prove, which identifies exactly which vectors are good. So the lemma is that if W transpose A minus Bi inverse W is less than minus 1, then W is B good. Okay, so if this quadratic form is sufficiently negative, then this vector gives me a new eigenvalue that shoots across the barrier. Okay. So let me prove this.
What's this? A minus B by?
A minus B times the identity.
I'm sorry, B?
Times the identity, Bi. So all matrices here are n by n. So this is a full dimensional identity. A is some not full rank matrix. Okay. So in particular, this matrix has some negative eigenvalues. So this quadratic form can be negative. Okay. So intuitively, what this is saying is that, well, you can imagine. I mean, this thing is positive on the span of A. It's negative outside the span of A. This thing is sort of saying if W is sufficiently outside the span of A, then adding it will give me a new big eigenvalue. Okay. So let me prove this. Okay, so the proof uses the so the proof is the following. So the proof is, consider the function trace of A minus Bi inverse. Okay.
Inverse is where?
Huh?
Inverse is outside.
Inverse is outside, yeah. Inverse is of the whole matrix. Okay.
Oh, no,
Inside the
it's not,
trace.
it's inside the trace.
Inside.
It's inside the trace, yeah. Yes, it's inside the trace. So okay. So what is this? Okay, here's one picture which is sort of guiding everything that's going on. So I have some B here. I have some matrix A that has all its non-zero eigenvalues ahead of B, and it has some zero eigenvalues here. Now, what are the contributions to this function? Well, all these positive eigenvalues are contributing some positive number that looks like this. So it's the reciprocal of the distance from B, right? And all these guys are contributing some negative number that looks like this. Okay? So just keep this in mind. Okay, so consider this function. Now, this thing is literally equal to the sum over all the eigenvalues of 1 over lambda I minus B, right? Okay, that's what this picture says. So now there's this fact, which, I mean, it's fairly easy to show. It's just well known. Is that the eigen? So let lambda 1, bigger than lambda 2, all the way to lambda k, bigger than 0, be the eigenvalues of A, and let lambda 1 prime bigger than lambda 2 prime, etc., be the eigenvalues of A plus W transpose. Okay?
You want to write, so lambda k you also know is bigger than B.
Yes. Okay, so this does have some assumptions. So this has the assumption that, lambda k of A is bigger than B, and lambda k plus 1 of A is 0. Okay?
No, I guess here you just wrote that lambda k is bigger than 0, not that it's
Oh, yes. Okay, fine.
protection is bigger than B. Okay.
Oh, okay, fine. It's bigger than B, but I guess I just want to say that lambda k plus 1 is equal to 0. I don't actually even need that. I'm just writing it to simplify the. Okay, so it's bigger than B. Fine, that's true. So it's bigger than B, but, well, I don't know. I guess I'm just writing that, fine, bigger than lambda k plus 1 equal to 0. How about that? Okay. And let these be the corresponding eigenvalues of this guy. So now there's this fact, which is that these eigenvalues interlace these eigenvalues. So lambda 1 prime is bigger than lambda 1, bigger than lambda 2 prime, bigger than lambda 2, and this thing is lambda k plus 1 prime. Okay? So what this is telling me is that if these are the eigenvalues of A, then the eigenvalues of A plus W transpose, lambda primes, these guys are all just shifted forward. And there's one more eigenvalue sitting somewhere in here. Okay? Okay. What is what?
Some vector.
W is some vector. So W is just some non-zero vector.
That satisfies this one? Or?
Yeah. If W satisfies this thing, then it's good. It it shoots an eigenvalue across.
So the interlacing W can be anything.
The interlacing W can be anything. Yes. Okay. So, is it okay to continue that over here? Okay, fine. Okay, so now let me evaluate trace of A plus WW transpose minus BI inverse, right? Well, this thing is equal to sum over I of 1 over lambda I prime minus B, right? So the point is, for I less than or equal to k plus 1, this is lambda I prime minus B, plus for the 0 eigenvalues, I know exactly what they are. It's n minus k minus 1 of these terms, which are just minus B. Okay. And actually, I can write this trace of A a little more carefully as well. There are k terms corresponding to non-zero eigenvalues, because that's what I assumed about A. And then there's n minus k of these terms just have minus B. Okay. Okay. So now what I can do is I can compute the difference. So if I look at this function on A and subtract what it becomes. Oh wait. I guess I want to do it the other way around. So right, yes. So if I look at the difference, this thing is equal to, so there are going to be terms corresponding to the non-zero eigenvalues of A and B. There's going to be at most k of those. So I'm going to get 1 over lambda I prime minus B minus 1 over lambda I minus B. And then I'm going to get this minus the n minus k thing. So plus 1 over B, actually. Oh, I'm sorry. What am I doing? Plus 1 over lambda k plus 1 prime minus B plus 1 over B. Okay. Okay. So now this thing is at most 0 because lambda I prime is bigger than lambda I. This thing is negative. So these numbers are positive. If I put this in here, I get lambda I minus lambda I prime. That's negative. Okay. So this whole thing is negative. Okay. So so in particular, if this change in trace, I'm going to call this thing delta trace or whatever. If this thing is positive, then can you see? Or then 1 over lambda k plus 1 prime minus b plus 1 by b must be positive, right? And now if you just look at this, if you rearrange this, you get that lambda k plus 1 prime must be bigger than b. Because you get this from looking at that picture of that graph over there. So if lambda k plus 1 prime is anywhere less than b, then this thing is actually, this number is more negative than minus 1 over b. So this thing is negative. So this thing better lie on the right-hand side of b. Okay? And you're using the fact that it's greater than 0, yes. You're using the fact that it's greater. So it interlaces the old eigenvalues and whatever, it's PSD. So this thing is greater than 0, and if it lies in the interval, if it lies anywhere greater than 0, then it has to be greater than b. Okay.
Very good. And I mean, if lambda k plus 1 prime is 0, then you get in the left-hand side 0.
Okay, fine. So let's get, if this is bigger than 0, then this thing is strictly.
No, it doesn't seem to be correct. I mean, so if lambda k plus 1 prime is half b, then you get.
No, you get negative. You get minus b. You get minus 2 over b plus 1 over b.
Yeah.
I mean, basically what happens is if it's, so at some point, so 1 over b is the value here. And if lambda is anywhere here, this thing is more negative than this thing. So it's like you're basically comparing the value at 0 to the value somewhere here. So okay. Okay. And now we evaluate this difference by some other method. So there is this thing called the Sherman-Morrison formula, which says that A plus W transpose inverse is equal to A inverse minus A inverse W transpose A inverse 1 plus W transpose A inverse W. Okay? So this is some basic fact about matrices that you can derive from block diagonalization or whatever. Okay? So I can also just take traces of everything.
So A plus W
Transpose inverse
is the inverse of.
is A inverse minus A inverse W transpose A inverse divided by 1 plus. So the inverse of the rank 1 update is the rank 1 update of the inverse. Okay, in this manner. I can take traces of both sides. And the thing is, when I take the trace of this guy, it also just becomes a quadratic form of W because I can move everything inside the trace. So I get W transpose A inverse, A minus 2W, right? So now I'm just going to apply this to my matrices here, right? So then I get that delta trace, this quantity which I computed here, is equal to, so the trace of A plus W transpose minus BI inverse is equal to the trace of A minus BI inverse minus W transpose A minus BI minus 2W 1 plus W transpose A minus BI. Okay, so this is minus, what it was before. Cancel, cancel. Okay? And now we see that this thing is bigger than 0 if W transpose A minus BI inverse W is less than minus 1. Because this thing is positive semi-definite, so this thing is always positive. If this thing holds, then this thing is negative. And so this whole thing must be positive. Okay? So that completes it.
Quadratic form of the numerator.
Yeah, so the numerator, this is a square of something. So this thing is always positive. It doesn't matter what A is. This thing is negative by assumption. So this difference is positive. This implies that the new eigenvalue is bigger than B. Okay? I mean, so this is just, really, this just comes from looking at that picture. But I guess you have to do this stuff too. I guess there are simpler proofs of it, but I have the one, the Sherman-Morrison one, we're going to use this again, actually. So
Generate it, just leave that.
okay, good idea. So, okay. So this suggests something. So we want vectors that are good, right? We want them to jump across B. And one observation. So by Lemma 1, let's say. By Lemma 1, if we take the average of that quadratic form over all the vectors and it's sufficiently negative, then a good vector must exist, right? So if sum over all I of Wi transpose A minus Bi inverse Wi is less than minus m, then a B good Wi must exist, right? So I'm gonna use this quantity to keep track of how I'm doing. So I'm going to define this potential function phi b of A to be equal to this thing, which I can write more cleanly in matrix notation as trace of L transpose A minus Bi inverse L. Okay? Because Wi are the columns of L. Okay?
So this potential function is a sum over all the Wi.
It's a sum over all the Wi's, but the point is, it's also just a trace of this matrix, but it's a sum of all the Wi's.
Including the ones that are already.
All of them, yeah. Including the ones that are already there, which are bad, but yeah. Okay. So, this suggests that, if I can keep this thing sufficiently negative, then there's always a good vector, right? So the problem is that when I add a vector, this potential increases by essentially an argument just like the one I showed you in the previous lemma. If I just add a vector, this potential actually increases. Because I gave you a new positive eigenvalue that gives a positive contribution to this sum, to this trace, and the number of negative eigenvalues is less. So what this is saying is that if I just add vectors, this thing deteriorates, and so I can't keep guaranteeing that there's a good vector, right? So I can't use this. So the way I fix this is by compensating for it by shifting the barrier backwards. That's why I have to shift the barrier backwards. So that decreases the potential. The reason it decreases the potential is because you get closer to 0. You get reciprocals of smaller numbers, negative or whatever. If you move this closer to 0, then this contribution becomes more negative and this thing becomes less positive. So it decreases. Okay. So the fix is I'm going to compensate by shifting b to b minus delta for some delta to be determined later. Now I'm going to look for a vector. So I'm writing sort of the outline of the main lemmas on this part here. So I'm going to define a vector to be b delta great if it's b good, and if I add it and shift the barrier, the potential does not increase. Okay. So this is what I'm really looking for if I want to keep going. So I want to shoot these things across the barrier with these good vectors, but I also want to keep that quantity sufficiently negative so that I can keep going. Okay? And now I'm going to prove a lemma which identifies when a vector is b delta great. So if W transpose A minus B minus delta I inverse LL transpose A minus B minus delta I inverse W is at most potential. This is phi B at A minus phi B prime at A times minus 1 minus W transpose A minus B minus delta I inverse W. If this thing holds, then it's great. Okay. So okay, this looks a bit weird, but what it's really saying, if you rearrange this, is instead of asking for this quadratic form to be less than -1, it's asking for it to be less than -1 minus something else. Okay? So this is a strictly stronger condition than this one. Okay? So, so notice that this thing implies that this thing must be positive, right? So this condition is equivalent to saying this is positive. This stronger condition is equivalent to saying that this thing times some number is actually bigger than some other number, which is bounded away from 0.
Both those terms are positive.
Yeah, so the point is both these things are positive. So this is PSD because it's something times this transpose. And this as I said, when I shift the barrier back, the potential goes down. So this thing is also positive.
B prime is B minus delta.
Yeah. Oh, yeah, I'm sorry. Yeah, B minus delta. So there's no B prime yet. Okay? Okay.
Normally, when you add another W's, a new eigenvalue is bigger than B or bigger than B minus delta?
B minus delta.
So the definition of B delta great is it should be B good or B minus delta good?
You're right. B minus delta good. It's a good point. Yes, correct. Okay.
So is there, can you read the first line of Lemma 2 in words?
First line, this.
Yeah, is there like a transpose somewhere on the right hand side? Because you said it was something times the transpose.
So if W transpose, so here we have A minus B minus delta I inverse L times A minus B minus delta I inverse L transpose, because this thing is symmetric. So this is some matrix. This is it times its own transpose. Okay, so this is some positive quadratic form. This is some positive number. This is something related to what we were looking at earlier. So this is some stronger negativity condition on this quadratic form in a way that depends on some other quadratic form of W. Okay. So now, again, so the way I'm going to prove that lemma is by Sherman-Morrison, basically. Like almost the same thing. So proof of lemma 2. So I have the potential at B minus delta of A plus WW transpose, right? This thing is the trace of L transpose A plus WW transpose minus. Okay, so I don't want to keep writing B minus delta, so let B prime be B minus delta, okay? Minus B prime I inverse L. Okay, this is the new potential. I'm going to use Sherman-Morrison, this same thing right here, to expand this. So I can write this inverse using Sherman-Morrison. So I get that this thing is trace of L transpose. So the point is that these L's don't interact at all with the inverse. They're outside the inverse. So I just apply Sherman-Morrison to the thing right in here. And I get L transpose A minus B prime I inverse L minus. Now here's where it gets a little different from the previous case. I get trace of L transpose A minus B prime I inverse WW transpose A minus B prime I inverse L.
You got a subtraction between the traces?
Yeah, so the point is, so I'm applying Sherman-Morrison to this thing in here.
So why, sorry, I'm slow on the linear algebra. Why can't you just stick it, the Sherman-Morrison in the middle? Like,
That's all I'm doing.
yeah, but how come it's
Oh, why can you?
like an L transpose and an L floating?
Oh, because this is actually not a statement about traces, it's a statement about matrices. Sherman-Morrison is actually, so the full form is that, you have this, you have A inverse W transpose A inverse. So, okay, I guess I totally butchered that, but you can,
You just can copy that.
yeah, you just copy this in here, and you just get this. So that's not what you meant, I guess.
No, just write the formula again.
Oh, write it again?
Archaeology, you have
Okay, fine. Yeah, I guess this is kind of messed up now.
Just erase the numerator and rewrite the numerator. That's fine. That's the only.
So when you take traces, that thing becomes a quadratic form. But now we're not allowed to take traces because we have these L's sitting around. So we get this thing instead. But the point, in the denominator, we still get the same thing because there's no L's in the denominator. So we get 1 plus W transpose A minus B prime I inverse W. Okay? Okay. Now, okay, so this thing is a trace, so I'm going to move this around and write this as a quadratic form. So should I erase it or should I write it again? Okay, fine, write it again.
You just want the left-hand side of lemma 2, right? Inside there?
Something like, yeah. Yeah, I just want the left-hand side of lemma 2. It's just the left-hand side of lemma 2, yeah. Okay, so maybe I don't even need to do that. So fine, so what is this? This is phi b prime of A minus, that thing is the left-hand side of lemma 2. This thing is,
Trace of the left-hand side.
well, actually it's equal to the left-hand side.
Oh, because it's scalar?
It's a scalar. I mean, this is, it's a quadratic form. So the trace of this thing is equal to the left-hand side because I just remove all this stuff over there. Is that okay? Okay, so this thing is equal to W transpose A minus B prime I inverse LL transpose, right?
And then it's a rank 1 matrix.
And then it's a rank 1 matrix. So you can remove the trace. It's a trace of a number. So
No, it's a scalar, not even an
Yeah, scalar.
it's a trace of a number, yeah.
Yeah, trace.
So it's actually equal to the LHS.
Again, I'm a little worried. You're not getting the same things. Here you have phi b of A minus phi b prime of A,
Mm-hmm.
and you're getting phi b prime of the expressions are not the same.
There's
Oh.
a B prime and a B versus a B.
Yeah.
Right. Oh no, I'll take care of that. I'll take care of it.
Then we can fix it.
Okay.
Sure.
So here I get 1 plus W transpose A minus B prime I inverse W, right? Now, this thing is equal to, so what is phi B prime of A, right? Well, it's phi B of A minus the difference. Right? Minus whatever this stuff is, okay? And so what I want is, I want this thing to be less than this thing, and so I rearrange whatever that thing is, and I get lemma 2.
Yeah.
So there is a sort of important point here, which is that the calculation I did there is only for what I need to do in order to decrease the potential, right? It doesn't tell me that the thing also, is B good, right? The reason it does that is because this thing is positive semi-definite. This is very important. So in one equation, we're able to guarantee two things. We're able to guarantee that the thing jumps across a barrier and it decreases the potential. I mean, those things they're not entirely independent. They obviously have a lot to do with each other, but
Why did it give you the second condition again?
because, so the point is this equation implies, it certainly implies that the potential doesn't increase by what I did there. But because this quantity is always positive and this quantity is always positive, it implies that this quantity is positive, which implies the first condition. Okay? So that's very important. So that's sort of how we're able to, essentially we just worry about the potential, but we sort of get, even though we're averaging over all these garbage vectors all the time, we are always guaranteed that the vector that we choose actually is linearly independent. Okay? So this being PSD is quite important. Okay, so
Maybe this was the question I was asking. This has like a B prime in the denominator, but that thing is. No, never mind. It's okay.
those things are all B primes.
Yeah, you're right.
B minus deltas. Okay. So this comes from rearranging, but yeah. So really, the most important thing about this is what I just said, that this implies the lemma 1 condition. Okay. Okay. So now I've identified what a great vector is. And now I'm going to prove so the main lemma is that if the potential is sufficiently negative, which I'll write here, then there's always a great vector. And that finishes the proof because that allows me to do both things. It allows me to jump across the barrier and keep the potential just as negative as it was. So, yeah, that's a good idea.
What's the contribution to the potential of the previous vectors that you already took for A?
Well, I mean, their contribution does change. So it does decrease because they may move forward. But this is saying the total potential does not increase.
And we know that they cannot be good, right? Because
No, they cannot be good because they're already there. Because they don't jump across.
I just wonder because it seems that for some choices of parameters, you really want to choose almost all vectors, right? If you want to really get
Yeah.
and then it looks strange that you still average over everything.
Well, so essentially the reason is, it's sort of given by this picture, right? So in that process, when the B becomes here, right? Then if I have a 0 guy sitting here, this thing is going to blow up. This thing is already pretty close. Maybe I'm writing it the wrong way, but I mean, actually this is the wrong way. The value here is already very negative. So this thing is really dominating. So suppose I'm at a point with the barriers here. I have a ton of eigenvalues sitting here, right? Now the potential, there's some positive contribution from these guys, right? But this 0 is really, really close to this. And so this is actually killing all of this.
Even if they are the majority.
Even if they're all but one. Not all but one, but even if they're all any constant fraction, actually.
Right. Because then you wouldn't want that the sum is less than minus m. It would be enough if the sum is less than minus the number of vectors that's left, right?
Yes.
And then still it doesn't matter.
It doesn't matter. So, essentially the point of this potential function is, well, really the main thing it does is it keeps track of what's outside A. But, it also happens to be a good way of making sure things are going on or jumping across B. But yeah, as you get this close to 0, it becomes very sensitive to what's outside A, which is why you can actually keep it that negative. So, okay, so the main lemma, or the induction lemma, or whatever, lemma 3 is if this potential is at most minus m minus the 2 norm over delta, then there exists b delta great vector. Now there's an additional technical condition that I'm going to put here, which will become clearer when we work out the proof of this. Okay, but basically this is it. So once I can prove this lemma, I can finish the proof of the theorem by just finding a feasible range of parameters. So to finish the proof of the theorem, so I'll prove that lemma at the end, but to finish the proof of the theorem, so the proof of the theorem will then be, I start off with b naught being equal to 1 minus epsilon times the Frobenius norm of L squared divided by m. And delta equal to 1 minus epsilon over epsilon times 2 norm over m. Okay?
So we already saw, so I guess lemma 3 suggests that delta should be L2, the 2
Yes,
norm.
yes.
But we didn't see why you have to start B at the Frobenius norm yet, did we?
Oh, well, okay, that's going to have to do the technical condition. So, but in any case, if I put this, it's not a technical condition actually, it's a very important condition, but it looks really weird if you just put it out there in the beginning. Roughly the condition is that B actually can't be too far out because, as I explained in that picture earlier, by moving B closer to 0, I'm keeping things negative, right? But if B is way out there, it's not going to be very sensitive to what happens when I move it closer to 0. So actually B needs to be within a very specific range, which is what the additional condition there is. But these parameters satisfy that as well as this additional condition, which anyway, so well.
And the additional condition for us would be just that the potential is negative enough, right? What we just showed.
Yeah, well, okay, so I might as well, I'm.
You want that the starting potential is negative enough.
Yeah, no, there's one more condition. So you actually need this additional condition that delta is less than B is less than delta times the Frobenius norm squared. Okay, I might as well just write this, because I keep mentioning this mysterious condition. Okay, if this and, so call this 1, and then there's another condition, which is that, so delta has to be positive. It has to be less than B. I can't make this thing go beyond 0. But B also has to be at most delta times the Frobenius norm of QLF squared over L2 squared, where Q is a projection onto the kernel of A. Okay, so this is sort of measuring the stable rank outside A, if that's what you. So initially Q is the identity, and initially this is the stable rank. So this is telling me that B had better not be way too far out, and that's why B has to be what I mentioned over there. So this is the additional condition, which, fine, I guess it doesn't look that weird, but okay. So if I set these things up, then well, I can check that 1 is satisfied. I mean, with equality. I mean, do you want me to do it? I mean, you just plug it in. It's fine. And to check that 2 is satisfied, you actually need to, it's not hard, but you need to say something. Yeah, so I need to do two things. That 2 is satisfied initially, and that 2 comes for free. As 2 is always maintained if it's satisfied initially. Okay, so here's why. So check is 1. Do you want me to do this?
So 2 is this thing that is not marked by 2.
Oh yeah. 2 is this thing. Sorry. 2 is this thing. Okay. So 1. I mean, okay. I might as well just do it. It's not such a big deal. So phi b naught of 0 is trace of L transpose L divided by minus b, I guess, right? Okay.
No, minus b squared.
Minus b. It's just inverse. Okay. There's no square on that.
No. There's an n
Well,
there. It's an n by n identity matrix. Right? So there's an n missing somehow.
No, but that's just multiplication.
So you have L transpose 0 minus b naught inverse L, right?
Yeah.
So this thing is just going to multiply.
Matrix, though, isn't it?
So B times A.
Yeah, but it's a multiple of the identity in particular.
Yeah, you can just take it out.
Yeah, you can just take you just get so you just get that. This thing is minus b naught minus 1 over b naught times the identity. Okay, so now I need to check that 1 is satisfied. So this is what the left hand side is equal to. The right hand side is equal to minus m minus minus what is this? L2 squared over delta. Now delta is equal to this, right? So yeah. So I get minus m minus well, I guess I should, okay, I might as well plug in what b naught is here already. So this thing divided by b naught is equal to m over 1 minus epsilon. Okay. And this thing is equal to minus m epsilon over 1 minus epsilon. Yeah, this is negative. And this thing is also equal to m over 1 minus epsilon. Okay? I just plugged it in. And minus. Everything's minus. Okay, so that means 1 is satisfied. So for 2 initially, Q is just the identity. It's a projection orthogonal to the kernel of A. A is initially 0. Projection onto the kernel, onto the kernel. Yeah. No, it's everything initially. Initially A is 0, so the kernel is everything. So what I need to, so I need to verify two things. So 2 has these two parts, right? B is bigger than delta and B is at most something. Okay, so yeah, so I'm going to need to do so first I need to verify that B is bigger than delta, right? How do I do that? I get that so let's see. So I have two cases. So in one case, I have epsilon squared times the stable rank. So in case 1, I have this thing is less than 1. So in this case, so recall that this is the number of things I wanted to get, right? This is the size of the set I eventually wanted to end up with. So actually in the statement of the theorem, the number of elements I'm going to get is floor of this. Okay, so if this thing is less than 1, the theorem says nothing. Okay, so okay, nothing. Okay, so assume that this thing is bigger than 1. Which gives me some lower bound on epsilon, which gives me some upper bound on delta. So let's see exactly what that is.
Exactly. The ratio of B to delta is like epsilon times or divided by the stable rank.
Exactly gives you that.
Well, that's okay. Epsilon squared is better than epsilon.
Okay.
It's less than 1. So beta delta is, okay, so it's the stable rank divided by epsilon. Okay, yeah, so epsilon squared is better than delta, okay? So this thing is checked. Okay, whatever. And the other thing is I want B to be at most, so I want B over delta to be at most the stable rank. Right? And this is also true if epsilon is like between 0 and 1, because 1 minus epsilon. Okay? And now the only thing you sort of need to say is that this value decreases by at most the 2 norm in one step. Okay. I'm adding, I'm removing one dimension from, A. How much mass is it going to have at most of the 2 norm? So in particular, if this thing holds initially, and delta is less than the 2 norm. I'm sorry, delta is greater than the 2 norm, which it is. then this thing continues to hold. So I need b to be smaller than delta times times this thing, right? And delta is, yeah, so that's fine. So you can forget about the m's because they appear in both b and delta. I mean, you can just cancel them. And this thing decreases by most of 2 norm. And this 1 minus epsilon over epsilon times this 2 norm squared is at least the 2 norm. Okay. Okay. So this means that 2, as long as you maintain 2 initially, you get it for free for the rest of the steps. And this setting does that. Okay. And so, is everybody okay with this, by the way? This is, I sense a bit of unease in the.
Can you see why this was true?
You don't see why this is true?
Yeah.
Okay. So I need b. Okay, so suppose I have b is less than. So in the first step, I have b is less than delta times the stable rank, right?
Just to make it official, you will probably not make a break, right? Because
Oh, should I? Oh,
Just continue.
my bad. Okay. So I want this to imply that b minus delta is at most delta times, the stable rank. So I want minus delta, right? This is what I want, right? And so if you just so I already know this part. So if I
No, there's a Q, right? I mean, this is the part I was asking about.
the q. I'm sorry.
You wrote the
Yes. Okay. Yes. Okay. So this is the part that's true. the part that we want is this, right? So now, so suppose Q went from being the whole space to something of codimension 1, right? This quantity, the smallest it could become is the Frobenius norm minus the 2 norm. Because I took a matrix, I projected at one of the dimensions. How much trace could I lose? At most at my max eigenvalue, right? And now we see that this thing is literally equal to the term before minus delta, which follows, right? Because you just cancel the deltas. So basically, in each step, you're not. I mean, this is why the 2 norm is important, because you're not eating away too much of the stable rank in every step, or too much of the Frobenius norm. Is this okay? Good idea. Yes. Yeah. So. Okay. So I verified that for these parameters, these conditions are satisfied initially. And I can continue this process. So suppose I want to take t steps, right? I can continue this process until these things continue to hold. Now this thing is going to continue to hold forever. But I got to stop when I get b bigger than delta, right? So after t minus 1 steps, right? The value is b naught minus t minus 1 times delta, right? Now I want this thing to be bigger than delta, okay? The point is I only need this to hold for t minus 1 steps, because in the last step, I don't actually care what happens after that, okay? I just need to add one vector, and then I don't care about the potential. I don't care. I just want it to jump across. I don't care about.
Does it matter the difference between t minus 1 and t?
Yeah, it does. Otherwise, you lose. You don't get floor. You get something slightly worse. I mean, if you want to really type. So then this gives you that b naught must be bigger than t delta. So t is at most b naught over delta, which is equal to what is B naught over delta?
It's epsilon times the stable rank.
It's epsilon times the stable rank.
Epsilon, why, oh, but you were saying epsilon squared. Okay. Oh, maybe your delta should have
maybe
1 over
delta
epsilon.
should have a delta epsilon squared.
No, then it doesn't work for the right-hand side of the initial.
Yeah, this is an epsilon actually, but in particular, if you take t to be epsilon squared times the thing, it's fine. So wait. You're right. No, this is a slight. So let's see. If I actually took t to be epsilon, what would I get?
There's also an epsilon squared, 1 minus epsilon squared for your.
For your like target, what you want.
Yeah. So maybe those should be
Right.
1 minus epsilons.
No, this is 1 minus epsilon. I mean, when you actually, so in the end, you're interested in the number b naught minus t delta, right?
Yeah.
And there's some funny interaction with the epsilons that happens there. I can show you what it is. But, I mean, this is just a statement b naught minus t delta is greater than 0, I guess.
Sure.
So I'm not doing anything.
So that's not the only. That's
not the only reason you can't go. You can't go below 0 either. You can't go below delta, but it turns out that with this step size, you can do both those things. Huh?
Never mind.
Okay.
This equation is not true.
Which equation?
Yeah, it just occurs to me that it's not true. If minus, is it?
No, that's okay. That's fine.
But epsilon is epsilon.
Yeah, I got
Is a minus here.
Got it. Yeah, got it.
It's a minus.
Yeah. Yeah. So everything's fine there.
Okay.
Okay, let's prove number 3.
Okay. So if I plug this stuff in, I get.
Oh, but you haven't proved limits. Okay.
Yeah, that's the main.
Yeah.
It won't take that long. It's just a lot of grunging. So, yeah, I have to prove lemma 3, but it's anyway.
So you start with a new board.
Well, okay. Do you want me to plug this in and show you that it gives you that number?
Which gives you the.
So the ultimate conclusion that we want is that we can take t equal to floor of epsilon squared times the stable rank.
Oh, okay. Sure. Why not?
Okay.
So the floor isn't so important.
Floor is important, yeah. Otherwise you can't get this guy.
Except for, basically it's for the 0 case.
It's for the 0 case, yeah, fine.
Okay, fine.
Okay, it's not that important. But, well, no, it is important, actually. Well, there's a difference of 1 step. If you get this number, I mean, there's a difference between the last step and going below delta.
I mean, then in some sense it's not tight because in the trivial case you should get 1 vector.
Yeah, but why?
In that case, it's not tight, but no, I mean,
care to get one less?
I mean, if you care. I mean, if you don't care, it doesn't matter. But if you care, then it should be floor. There is a difference of 1 vector.
Yeah.
In case.
You care what vector.
I mean, why not, right? So, okay. So if I take this many steps, then the final value that I end up with, okay, is 1 minus epsilon times the Frobenius norm by m minus epsilon squared times. So so in the end I get this thing at least. So then I remove the floor. I get this thing
there's
times.
An epsilon times 1 minus epsilon.
Yeah, 1 minus epsilon divided by epsilon.
So the epsilon squared goes away.
Yeah.
And the 1 minus epsilon. Yeah. Okay.
And then there's some others. Yeah. So I get times 1 minus epsilon divided by epsilon times 2 norm squared divided by m. Okay, so what is this? Okay, so cancel. So I get 1 minus epsilon times the Frobenius norm squared over m by 1 minus epsilon, yes, which is what I said we get. Okay, so now we have to prove the lemma 3. Is this okay? Okay. So now I have to prove lemma 3. Okay, proof of lemma 3 is you want to show that if those conditions hold, then some great vector exists, right? Proof of this is also by averaging. So where is lemma 3? Well, okay, I'm just going to take the sum of that equation over all that inequality that I want over all the vectors. What am I going to get? I'm going to get trace of L transpose A minus B prime I inverse L transpose L less than, so here I have, this is some constant, doesn't enter into the sum. I'm adding over m vectors, I get minus m minus, if I add that quadratic form over all the vectors, I get trace of L transpose A minus B prime I inverse L. Okay, and this quantity is just the potential at B prime. So I'm just,
We just took lemma 2 and summed it up.
yeah. Yeah, we just added it over, so sum over all vectors. So this is the desired inequality here. Okay. Okay, so this is what we want. Now a couple of things. So by the first assumption, we have that phi b prime of A is at most, so we know that phi b of A is at most minus m minus this thing, but phi b prime is at most this thing minus, I'm going to call this quantity delta b. So delta b is, well, delta b is just this guy. So let me just call this thing delta b. Okay, delta b is phi b a minus phi b prime a. This is the difference in potentials when I just shift the barrier. Okay, so by 1, this thing I'm interested in here is at most this thing which I got from 1 minus, just the difference from shifting. Okay. Also, okay, the left-hand side over there is at most the 2 norm of L squared times the trace of A minus B prime I inverse LL transpose A minus B prime I inverse. This is because this matrix is positive semi-definite. So if I multiply it by some other matrix, the trace is bounded by, whatever this is times the norm of that matrix. The norm of that matrix is this. Okay. Okay. And I'm going to write this thing as the norm of L. So I'm just going to move things around inside the trace again. L transpose A minus B prime I minus 2L. Okay. So let's see. so it suffices to show. So just plugging these two observations into what I wanted to show, it suffices to show that L2 squared that this thing is at most so delta B times so minus m minus this thing, which is at most
Well, it's just that L squared of delta minus delta.
Delta B is positive.
At least
delta B is positive. Delta B is positive. So delta B prime. Yeah. So this quantity is bigger than if I replace this by that.
Yeah.
And so what I get is okay. So if I show that, then it's good. So now I need to do this slightly. Okay, so here's okay. So a minus b prime I is not positive semi-definite. Okay, but if it was, then the following thing would be true. It would be true that a minus b prime I to the minus 2, rather delta times this, is at most a minus b I inverse minus a minus b prime I inverse. Actually, this would be a positive semi-definiteness relation.
So actually, is that an A prime or is that just A? That's A, right? A minus
A, yeah, A. So if if a minus b I, if this thing was positive semi-definite, this thing would be true.
I don't see why do you need this. So all of them are simultaneously diagonalizing.
Yeah. So it's just a statement about numbers.
So it's just yeah.
So
let's
so what would this statement be? So this would, you want to prove that 1 over lambda I minus b prime squared
delta.
is at most.
So there's a delta.
Yeah. So the delta is just b
B minus B.
b prime. And here you would have 1 over lambda I minus b prime minus 1 over lambda I minus b minus b prime, right? Okay. Now the point is this thing. Okay, so this is what you want. So the point is this thing is equal to b minus b prime divided by lambda I minus b over lambda I minus b prime, right? Now, if these numbers are positive, then changing a b prime to a b makes this number smaller, which makes this number bigger, so this whole thing is correct.
Sorry, are we still working under the fictitious assumption that
Yes.
this thing is PST?
Yeah.
Are we going to try to still prove this PST inequality anyway, or we're going to try to prove?
Oh no, we're going to split it into PSD and 0 parts. Actually, I'm not sure why I'm presenting this fictitious inequality, come to think of it. Okay. But, well, okay. Well, part of the reason is that initially, we didn't realize this and we just did it. And this is how we got this number. And we're like, oh, okay. But then Pete Casazza found this bug and then we had to fix it. So, anyway, I guess I'm just trying to explain to you why you need to split it into positive and 0 parts. Maybe you don't, I mean.
What is the positive and 0 parts?
So I want to bound this thing by something like delta B divided by delta, right? The point is that, it looks like something like this might be true, but I just wanted to say you need to do something different for the kernel, which is where that additional technical condition comes from. So if this thing was actually true, there would be no number 2 condition. Because I would just have, like, that inequality implies that this thing is at most this quantity, right? So clearly if I add something positive, it's still true. Maybe this is, maybe I'm just presenting it this way because historically this is what happened. But I guess I want to give you some intuition as to why these. So I am going to use this on the positive part, so it's not a complete waste. So I guess the point is that if the lambda i's are the lambda i's are 0, so lambda i's are less than b, then this thing doesn't work anymore.
So are there lambda i's and lambda i primes? Just kind of. Oh no, you're still with a. Sorry, you're always with a.
Well, okay, fine. So why don't I erase this fictitious thing and actually show you something that's true? So here's what's true. So let P be the projection onto the image of A. Okay. Then and let Q be the complement. So we have that P, Q, A minus B prime I inverse, etc. are they commute. Okay. So in particular, what this means is I can write trace of A minus B prime I inverse as sum. Oh, there's no sum. It's just as trace of. Trace of L transpose. So this is my potential as trace of L transpose P A minus B prime I inverse P L. Plus trace of L transpose Q A minus B prime I inverse Q L. Okay, so I'm going to call these things the potential on P and the potential on Q. These are just the contributions from the. This is just a way of writing that there are different contributions from the 0 eigenvalues and the ones that are bigger than B prime. And the thing which I wrote earlier, which I erased, is that it's the statement that P A minus B prime I minus 2P, this thing, so delta times this thing is at most P A minus BI inverse minus A minus B prime I inverse P. So this is the thing which I just said earlier. This is some statement that's true for positive semi-definite matrices, which these are because I applied the P's. Okay? So I killed all the 0 eigenvalues. Huh?
Strictly positive semi-definite?
They have a lot of zeros, but the zeros don't change, so it's okay. So what this means is that if I take traces of these, if I multiply these sides by L by L transpose L and take traces, I get something like L transpose delta L transpose delta trace L transpose P A minus B prime I minus 2 P L is at most. If you plug all this in, you literally just get the change in potentials computed only on the subspace P. Okay. Now, the term that we're really interested in is this, right? And this, just like everything else, I can break into a P part and a Q part. Well, fine, I guess I might as well write it. So you have a P part and a Q part. Okay. And what I've done over there is I've bounded this P part by something over here. Okay. And so, okay, so call this thing delta. So I have the delta b's. I'm also going to split these into p and q parts. So now, so plugging this in. So plugging into the thing we want to show, it's well, it doesn't have a name. It suffices to get that it suffices to just deal with the q part, basically. So it suffices to get L squared trace L transpose Q A minus B prime I. Suffices to get this thing at most. So this is the quantity we're interested in. And I just showed that the P part is at most delta B, is at most delta B over delta. So
L2 squared.
there's also an L2 squared, yeah. So there will be an L2 squared. So what I'll get is delta P delta B P plus delta B Q. Times this guy plus, well, delta Bp plus delta Bq minus delta Bp times the L2 part divided by delta. Okay? So now this is going to cancel this term here, and I'm going to end up with a statement, and I'm going to sort of discard this P term. I'm going to end up with a statement just about Q terms, and rearranging it is going to give me the second condition. You want me to do it? Yeah, okay. So okay, so right, so I want the, okay, so I'm going to cancel the P terms, and I'm going to forget about the product. Okay, so what's going to happen is this and this are going to cancel, okay? And I'm going to forget about the lower order delta BQ, delta BP term. I'm just going to have,
delta BP.
well, okay, there are going to be some more. Okay, I might as well just open it and just, yeah. So, okay, so I want trace of L transpose Q this thing to be at most. Delta Vp times, okay, so I'm just going to open this, times delta B Q plus delta B P squared plus delta B Q L2 squared divided by delta. And there's also, right, plus delta BQ times just delta B. Let's just say that. Okay.
Q squared. So it's like,
Oh, well, the Q squared is in there.
The Q squared's in here. Yeah.
so it's delta B squared.
I mean, I guess I could have just written delta P delta B here, right? So that would have been fine too.
Delta B squared.
It is just delta B squared, yeah. So I'm going to ignore some part of this. Let's see, what part of this am I going to ignore? Well, at this point, I'm just going to plug in. I'm going to compute exactly what these things are. And then let's see what happens. So you just compute. Okay, so the LHS, probably should have done this earlier and saved myself writing this horrible expression all over the place. That thing is just going to be the Frobenius norm of QL squared divided by B prime squared. Okay? The left hand, this guy is literally just equal to this. Because when I project out A, all I get is some multiple of the identity on that space multiplied by B prime, which I then square. Okay? And now I have some term delta BQ, which is going to be equal to, so yeah, I probably should have done these simplifications earlier. So the old potential contribution from Q is something like this, minus the same thing over B prime.
There's a minus
I
one.
think that's right.
It's the negative of
It's a negative of this. Okay. Okay, so this thing is equal to so you get a you get a delta and you get a B prime. Okay. Now what exactly am I gonna ignore here? Do I really need all these terms? I need to show, okay, so I have one more assumption. So what's my number 2 assumption that I have over there? It's that delta, it's that B is at most delta times, so I also know that B is at most delta times that, okay? Okay, so, well, okay, maybe this is the wrong way to do this, because ideally we should have just messed around and arrived at this point, right? So maybe I should do that.
No.
But okay, fine. I mean, that's how it came out, I guess, but I don't remember what term. Okay, so what term should we ignore here? So the lower order term, I guess, okay, we should probably just ignore this guy.
And you can because it's positive.
It's positive, yeah. So you can ignore this. And now if I just plug everything in, I'm going to approximate this by delta VQ squared. I'm going to upper bound this by delta VQ squared. Is that reasonable?
Lower bound. You can lower bound it by delta BQ squared.
No, I mean, so if I can see this thing is equal to delta VQ times delta VQ plus the thing with the P term, right? I'm going to ignore the P term.
Yeah, that works. That's okay.
So it's okay. So I guess it's enough to show that, let's see, QL. This thing is at most times
L2 squared over delta.
times, this is a little weird, but anyway,
Plus delta Q.
plus this thing squared, right? Well, I guess I should just take this guy out, because that's probably the best thing to. So I'm going to take this. Oh, I could have just put a bracket. Okay. So you get L2 squared over delta plus the same thing again. Okay. So now what happens here?
B primes, one B prime comes out.
So these guys come out. One B prime comes out. So this cancels here.
Oh yeah.
And I get, okay, what happens here? So this I get a delta squared. Okay, so at this point, this thing is just delta over b, right? So I get L2 squared over b plus delta squared over b squared b prime, right?
And that's 1 over what?
It's 1 over b prime. Okay. Okay, so the ratio of interest here is delta over b, right? Oh, so b prime is b minus delta. Okay, wait a minute. So,
Use this condition now.
okay, fine. I guess we'll use this condition.
This will give an inequality from 2.
Yeah.
So multiply by
Oh yeah, yeah.
So just plug it in.
multiply by b prime just to get and
Okay.
make this will be minus one. Oh, same.
Yeah, good idea. Okay, so now we want this.
We can use the b by delta
Yeah.
Well, yeah.
and upper bound on lower bound on delta by b.
Yeah.
yeah.
I'm kind of running out of gas
No,
here,
no,
but
it's,
let's.
you just plug it in the right hand term.
Yeah.
So
I mean, it works out in some way. Fine, let's do it.
you get delta over b and L2 squared, which
Uh-huh.
is exactly 1.
Yeah. So
So you could have ignored the first term too.
Huh?
no, I don't think so.
No.
You need the second. You need that. You need both these terms.
So when you plug the assumption there, you get delta over b and L2 squared, and the sum of the two terms is 1. Is L2 squared. Which is
Um.
Draw a little box.
The right term becomes 1 like that.
Huh?
Draw a little box.
Draw a little box.
There's an L2 squared over
Huh?
B.
There's a delta squared over b squared.
We have delta square root. Oh, I see.
Okay, fine. So let's just plug that stuff in. So it suffices to show that. So what do you get when you get an L2? Okay.
So if you plug
So
that in, you get delta over b times L2 squared.
If you plug that in here, you mean?
So
Means
just
just
I mean take out one factor of delta over b and replace that with the lower bound that we have.
Oh, okay. Take out one factor of delta over b. Okay. So now we get b prime L2 squared over b plus L2 squared over this stable rank or whatever times 1 over delta, right? Okay.
No, you're
And
not,
now you gotta
you're
put
not
the
plugging
term
the
in.
multiplication.
Oh, okay, fine. So this is just that term, and now you have the delta over b, and then you have this guy again.
There's a delta squared
There's a delta squared.
in the numerator there. The numerator should have a delta squared.
No, I took one of those guys out.
Yeah, but then you shouldn't have written the extra delta in the denominator.
Mm-hmm. Yes. Okay, that's true.
No. Just leave one there.
Okay.
No. Get rid of the one in the denominator. Leave the one in the numerator. Then.
Okay, cool. Yeah,
No.
I'm actually, I can't think anymore.
There's a delta in the numerator and no delta in the denominator.
Okay, got it. So then, then what happens? I think I just gone about this the wrong way because I feel like there's a quick way.
There's a b prime, which is a b minus delta, on a
Yeah.
So that delta-
Oh, so it cancels. So this term is common.
So you just get L2 squared,
It just adds up to it. That's it.
which is
Okay.
kind of weird because it should be scale independent.
Oh, no, but there was an L2 squared that multiplied everything on the left.
There should be an L2
There's
squared here
L2
also, right?
squared on the left.
Yeah,
There should be an
multiplies
L2.
all of these things.
Oh, okay. So then everything.
Okay. So,
So on,
well, okay. If you want, I can think about it carefully and actually get it in a nice way. But I,
That's why you should have taken a
Yeah,
break
we'll
one
begin.
time.
huh? Yeah. So anyway, you rearrange it, you get the second condition, and then you just put it in the inductive hypothesis, and it happens to be maintained automatically. So you're all set.
You want to say so about the partition, the paving, is there any hope that this could lead?
Not really. So for the partition, you have to. I mean, not really. I mean, there's no clear. So if you want to actually do a partition, then you can't do this sloppy averaging over all the vectors. So if you want to somehow build a bunch of, you want to build two sets that have good properties, you sort of have to sample without replacement. And then you get then in all these averages, you get traces of, I minus the other thing and these kind of terms. And I mean, I don't know, we tried for quite a while and don't know how to deal with it. So I think the rough idea is that, I mean, if you compare this to this paper that we had on sparsification, it's sort of similar, but it uses one barrier. And the basic idea is if you want to, okay, what does it mean to have a partition, right? It means that if both sets are well invertible, it means that the first set has singular values bounded away from 0 and also bounded away from 1, because the complement has to be bounded away from 0. So that means I need control on the top and bottom eigenvalues. That means that at some level I either need two barriers or I need to do separate barrier arguments for different partitions. And I don't know any way to do this without averaging over some vectors that depend on what you've already done. So the reason this is, well, relatively clean, except for this part, is that you can always just take averages over everything and it's just some like clean trace. But if you start taking trace multiplied by I minus A or something like that, then you really have to worry about, I mean, I don't know how to manage that. So.
Here a fractional version follows automatically. So normally between the composition and getting one set, you can ask about the fractional version, that you give weights to the columns.
Yeah, so if you want fractional, you can do it with two barriers, for example. So the point of this is that you always pick a vector. You don't scale the vector when you pick it. If you're allowed to do that, then you can do basically this graph sparsification kind of thing, which is similar to this, in which you have two barriers, but then you're allowed to pick vectors with weights, and then you can satisfy both of them. And you can basically extract something that's bounded away from 0 and 1, and therefore so is its complement. So the thing here is you can either get unweighted or you can get upper and lower bounds. I don't know where to get both.